Hello and welcome to York Observatory's monthly TeleTube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. Tonight, we are broadcasting live from the Alan I. Carswell Observatory, located at York University in Toronto, Ontario, Canada. York YouTube broadcasts every last Friday of the month at 7:30 p.m. local Toronto time at this YouTube channel. For any questions or comments you have of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Instagram with the handle at Yorku Observatory and Facebook at Alni Carswell Ops. Our Astronomer in Residence program, in collaboration with Killarney Provincial Park, has come to an end for this year, and applications will reopen in 2025. If you're interested in learning more about the program, our past astronomers in residence, and their experiences, check out our website at yorku.ca/science/observatory/air. Good evening, everyone. I'm Maheen, and tonight I'm joined by Hector and Dave, and we're here from the Alan I. Carswell Observatory at York University. Tonight we have a guest speaker joining us who will be talking all about exoplanets. Dave will be introducing our speaker, Paul Mackin, shortly, but before that, I would like to make a land acknowledgement. The observatory at York campus is in Toronto, and we would like to welcome you all to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many Indigenous nations. The area known as Takaranto has been caretaken by the Anishinaabe Nation, the Haudenosaunee Confederacy, the Huron-Wendat, and the Métis. It is now home to many Indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of Credit First Nation. Our stargazing and astronomical efforts join the long history and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area. I'm now handing it over to Hector, who will talk about some interesting objects up in the sky this week and how to spot them. Over to you, Hector.
Well, welcome everyone. Before we get started with our main show, we want to give you a little update on in what you can see tonight. In terms of planets, tonight we have Saturn and Uranus slightly less, but fair enough. Jupiter will rise later at 8:42 p.m. Saturn has already risen, and you will be able to see it between the Sud and Sodis close to the constellation Aquarius. And Uranus, you should be able to see it between S and Northeast, almost between the constellation Taurus and Cetus. Moving on with our moon, its current phase is waning crescent, approximately 40% enlightened, which also has a guest close to it, the star Regulus, the brightest star in the constellation Leo. For more visible objects, there are plenty of asteroids like 1 Sirius, close to the constellation Sagittarius, and 1036 Ganymede, close to the constellation Pegasus, which will be visible during the nighttime with binoculars and some of them with a small telescope, as well as Uranus, besides Jupiter and Saturn, which are visible by the naked eye. Also, it seems that the comet A3 Tsuchi-chan Atlas is still visible between the west and southwest within the body of the constellation Ophiuchus, hopefully still visible by the naked eye. Now, I will hand it over to Dave to introduce our speaker tonight.
Hello, everyone. My name is Dave, and I'll be introducing our speaker, Paul Mackin, today. Paul Mackin is a telecommunications engineer and entrepreneur who, upon retirement, chose to return to university to study astrophysics. He is now in his second year of undergraduate physics and astronomy program here at York University. Welcome, and thank you for being with us today, Paul.
Thank you so much, Dev. I'm going to take over the screen here and start my presentation, I think. Thanks. Okay, 1 second here. And all right, we should be good. Good. Okay. Hi, everyone. As Dev said, I'm Paul Mackin. I'm a second-year student in the Department of Physics and Astronomy at York. And I'm going to talk tonight about exoplanets. A couple of years ago, there was much controversy about whether there was 8 or 9 planets in the solar system. And at that point, oh, it's not a video, sorry. I didn't quick, oh, someone's connected my face to the screen, which I don't want. Hang on. Give me a moment here, technical difficulties. There we go. Okay. Uh, so, yes, a couple of years ago, there was this controversy about removing Pluto as a planet. And it was always a bit silly because around the same time, we were discovering more planets than people could have possibly imagined. Let's talk a little bit about the history of things. So once upon a time, and this is an image from the Farmer's Almanac, when I was a kid in school, in public school, and that would have been in the 1960s and 70s, so a long time ago, this was kind of the classic image on the wall in the classroom. It showed, the planets, the sun, none of it to scale. Uranus did not have rings back then. And of course, all 4 of the gas giants do have rings. Pluto was definitely a planet. And no one really knew how big it was. It started off as kind of original projections where it was kind of Neptune sized, and then it appeared to be much smaller when it was discovered, and it shrunk down to the point now where it's not really considered a planet. So there were no planets, no dwarf planets, which is what Pluto is. And we didn't really know. We appeared to be unique in the universe. And every time we thought, as a species, humanity has thought we're unique, we find out we're not. Whether that be in the center of the universe, near the center of the galaxy, the only life, or only solar system, or only stellar planetary system out there. We always get a bit surprised when we start digging down a bit deeper. So there was the mystery of Barnard's star. This is a small, dim star, approximately 6 light years away. And in the early part of the 20th century, people noticed that not only was it moving, it had a high radial velocity, and here you can see pictures of it's taken moving against the background stars. It's really moving with respect to its neighboring stars. But in addition to the high radial velocity, it also seemed to have a little bit of a wiggle, which might indicate a Jupiter-sized planet orbiting it. But subsequent analysis indicated no planets. And that's where things stuck for quite a while. And then in 1988, the first suspected exoplanet was detected, and it wasn't confirmed till 2002. So what's that? 14 years later, and it was detected using a method that we're going to talk about in a minute, called the radial velocity method. Okay, by the end of the century, there were 8 more planets discovered. But the technique started getting better, and we started applying new technologies, and the floodgates absolutely opened. So today, there are more than 5,000. This was something unheard of in the 1980s. There are thousands of exoplanets. The targets have been identified and confirmed. There's new discoveries every single week. And it says here 5,000 in this image from JPL, and we'll come back to this image. But I checked, and early in July, the number was 5,780. And a lot of astronomers believe that almost every star has some planets. So that means if you look at there's billions and billions and billions of stars in a lot of galaxies, billions of galaxies, you've got a huge number of planets. So that's an important leap forward, because we've gone from this idea that maybe we're unique or planets are very rare to they're absolutely commonplace. But of course, they're all very special as well, and we'll talk more about that in a moment. So how did we get there? Well, we had techniques, we applied technology, and it took a lot of tenacity. This is a huge ongoing effort. So there are a number of different methods, and we're going to concentrate on three of them today, two that are commonly used and one that's a little more theoretical, but the technology is maturing. And there are others, but we're going to focus on these first three today. The radial velocity or the Doppler method, the transit or the eclipse method, and direct observation via a coronagraph, which we'll talk about as well. So I want to show you a little video here of the radial velocity method. And this is leveraging Doppler shift, and it's akin to when you're outside and you hear a motorcycle drive by. As the motorcycle approaches, the frequency goes up, and as it moves away, the frequency goes down. So this is what it sort of looks like if you look at it from a light point of view. I'm just going to make this a bit bigger on my screen here. So here you can see a planet going around a star, and as the planet is moving away from us, the reflected light is shifted to the red. And as it moves nearer, it's shifted to the blue. And we've got very accurate spectrographs. Remember, I mentioned the technology had gotten very mature. So we've got the ability to, really finely detect these changes, and that gives us the ability to develop planets. But so I'm going to look at the other method, and I'm going to tell you something both methods have in common. So the second method is the transit method, and this is a bit like eclipses. As you can see here, we've got the brightness, and when a planet goes across the face of the star, it dims the star slightly. So that is what's called the eclipse method. So, but both of these assume that you've got the planet and the star relatively, the planet relatively edge on to Earth with respect to the star. Not 100%, but in the eclipse method, it's got to eclipse the sun. It's got to cover at least part of the star. And in the transit method, it has to be enough that you can get the sense that it's moving away. It has to either be moving away from us or towards us to be able to have those frequency redshifts or blue shifts, those optical frequency redshifts or blue shifts. Another method, which is more interesting and would really open this up, is the coronagraph exoplanet detection. So here's an image of a spacecraft, a big space telescope with this big sunshade in front of it. Now, this is not to scale. To give you an idea, the coronagraph, the suspected distance away would be, very far, like thousands of kilometers away, and it's a big coronagraph, and it's designed to block out the light of the star. And here you can see this is actually a recreation of one, but you can see here we blocked out the light of the star, and you can see that there are planets, and this is actually a real detection, moving around it. The advantage this method has is it allows us to see planets that directly and that are not necessarily in the same plane as us, which the other methods require. So how did we get so many planets? Well, the Kepler Observatory, which was a mission dedicated to finding exoplanets, was the most prolific at finding them. Between 2009 and 2018, Kepler found 2,662 exoplanets. That's confirmed exoplanets. Now, it did it using the transit method, the eclipse method we looked at. And the way it worked was it stared at a single part of the sky for a very long time and measured the brightness of all the stars it could see. And here you can see there's this square on the image here that you can see there's kind of these little squares. This is the area it was looked at. And where it saw light changing, and there's no atmospheric effects or anything else in space, no weather to worry about, and the spacecraft was kept very cold, so the sensor that minimized quantum fluctuations on the sensors and so on. It was able to tag stars for follow-up, and those were confirmed by Earth-based telescopes. So this was an incredibly prolific mission. So the question is, where are these planets and what are they like? Now, I've hinted at this a little bit already. Our methods direct where we're finding them. So I talked about right now we're really good at finding planets that are on the same plane as Earth with respect to their star. Okay, but there's other features as well of the stars themselves that drive how we detect planets. So this is a a Hertzsprung-Russell diagram. Astronomers love this, and as a second-year student, I can tell you we get tested on it a lot. But this basically is a way of classifying stars by their brightness, their color, a couple of other things like the spectral class and absolute magnitude. But there won't be a test on this after the podcast today, but you can see here that most of the stars are in this single line. This is called the main sequence. These stars here are off the main sequence. They're stars that are approaching the end of their life, perhaps. These are stars that have reached the end of their life, white dwarfs. So the stars we're mostly interested in would be along this line here. Now, stars come in many types and sizes, and this is what this diagram shows. The sun, our sun, is really quite ordinary. In fact, it would be about here on the HR diagram. Larger stars are brighter, they're more active, and they die younger. So they're hard to spot planets around. First of all, the planets are small compared to the relative size of the star. Okay, so you don't get you won't get necessarily the eclipse behavior you want. Also, there's some issues because they're very close. The relative distance between them means that you might not get the radial variations that you would as well. Plus, these stars come into existence really quickly, which means their protostar phase is short and they're bigger. They pull more material in. There may just be fewer planets around these types of stars. So we're not going to focus on this end up here, but we can focus on smaller, dimmer stars because planets are bigger relative to those stars. They're going to be closer to the star, so they're going to move really quite quickly around the star, and thus it makes it a little easier to find planets. So stars down here. And this is an area of real interest because these stars also live a long time. Our sun is good for about 10 billion years, and it's about halfway through its life. But some of these stars can live 500 billion years or longer. They're very, very long lived, but they're small and dim. So, neither exoplanets are all different too. It's important to understand that the methodology we use to detect exoplanets, because what they find is bigger stars, bigger planets that are closer to smaller stars. So the planetary systems we're seeing are generally not like ours. They have a lot of hot Jupiters, really big planets, very close to the star, orbiting in days or hours even. There are super Earths, so something smaller than a Jupiter, but kind of bigger than Earth. And there's very few planets we find that are like our planet in terms of size. In fact, back to this slide, breaking this down, you can see here that the most common thing we find are what are called Neptune-like. Okay, these are similar size to Neptune and Uranus. They can be ice giants or warmer. Warm Neptunes are more rare. Then there's a lot of gas giants. These are very, very close, and they're often detected as very close to the star. They can be really, really hot. There are super Earths. These are planets between our size of Earth and the size of Neptune. And then so that's about 1/3 each. Oops, sorry. And then a very small percentage would be small terrestrial rocky planets, kind of like the size of Venus or the Earth. Maybe a little smaller or a little bigger, but there's not many of those. And it's because our methods of finding these planets really aren't optimized to detect them necessarily. So, this has gone from the most leading edge of science to something more mundane. It's been an absolute revolution in planetary astronomy. In less than 40 years, we've gone from 9 planets to nearly 6,000, even though we lost one in our own solar system. We can now, under certain conditions, even examine the atmospheres of exoplanets. In fact, undergraduates here at York University are exposed to the principles of exoplanet detection in their first year. And in their third year, they do an exoplanet detection project at our observatory, at the AICO observatory. They actually do a project to detect exoplanets. So, it's gone from something that is absolutely leading edge research to something that students do and learn how to do regularly. The next decades will bring further incremental growth in our understanding of these extrasolar planetary systems. But we have a lot of unanswered questions. How common are planetary systems like ours? Well, so far, and again, this may be the methods we're using to detect them, not that common. Okay, I'm personally believe, based on nothing other than my opinion, that they're actually relatively common. But there's so many different stars out there that you're going to find a lot of variance, and we're right now structured to find certain types of variance of stellar planetary systems. So another question, and a really big one, is how many of these are in the planet parent star's habitable zones? And we'll talk more about that in a second. And how many systems are processes excluded from detection? Because again, we've optimized our systems to find certain types of planets. And here's the big one. Are any of these planets, are any of these planets which can or do support life? Is there life out there on one of these planets, or are they capable of sustaining life? And again, we may talk about that when we get into our questions a bit. So there's really a lot of development in this space. There's some upcoming projects. The Nancy Grace Roman Coronagraph, the Nancy Grace Roman Telescope, this is an image of it, is going to be launched in 2027. It's not looking for exoplanets. It's looking for a whole bunch of different things, but it is taking up a test suite of coronagraph technologies, and it will assist with direct imaging of planets. But this is the first step. We're still trying to get these technologies developed better. There's also a whole bunch of next generation planetary detection tools coming online. The Nancy Grace Telescope will provide the first of these. NASA has also proposed a habitable worlds detection observatory. The ESA and JAXA, the Japanese Space Agency, are launching Plato, and the ESA is launching aerial missions, and they're coming up, I think, in Plato's 2025 or 2026, and Ariel's a little later. It's like 2028. But I'd like to add one final note. Bernard's star, after years of explanation, and this was really recent, this just happened in the last couple of weeks, Bernard's star was finally confirmed to host at least one exoplanet. So the planet, the star that was most suspect for this over 100 years ago, it has been confirmed to have at least one exoplanet. So thank you very much. And at this point, I'll turn this back over to my colleagues for any questions.
Thank you so much, Paul. We really, really enjoyed your presentation. It was a lot of fun. I'm sure it's been quite informative for all our speakers as well. Audience as well. We do have a few questions. I will hand it over to Hector to start us off.
Hello, Paul. Thank you so much for the impressive presentation about the exoplanets. Definitely one of the most fascinating hot topics currently in terms of universe observation. Now, let me ask you, Paul, can you how do astronomers differentiate between a true exoplanet and other cosmic phenomena that might mimic the signals of an exoplanet?
Yeah, that's one of the big challenges, Hector, in finding exoplanets is false positives. There can be a number of different phenomena. First of all, just bad data. And you have to understand that the signal differences we're looking for are very, very, very small. And of course, the smaller the planets, the less extreme, the circumstance of the planet being close to the star and its size, the more suspect it is. So finding, you could be glib about it and say finding exoplanets is relatively easy. Confirming them is the hard part. And you'll note when I went back to that very first exoplanet, it was 14 years from first detection to confirmation. So you get a lot of false positives in the data. You really do. I hope that answers your question.
Excellent. Thank you so much, Paul. And yeah, absolutely, you answer correctly. Fortunately, we have enough data to do the differentiation. Thanks so much, Paul. And other question, Paul. Let me ask you, can you describe the significance of the discovery of the very first exoplanet and how it impacts our understanding of the universe?
Yeah, it's a very good question. It's almost a philosophical question, Hector. But I remember, because I'm a bit older than your average student, I guess. I remember that the announcement of that first detection, and we'd had the sort of false story of Bernard's star for a long time, and then it went away. And then there was this really interesting candidate found, and it was done by the radial velocity method, the Doppler method I talked about. Um, and people were speculating, okay, we found one, but is this just a one of, and we're still pretty much a unique case, or um, is it the first of many? And so there, as more and more planets, nothing succeeds like success. As more and more planets got discovered, this caused a groundswell, which allowed for the funding of observatories to look for these exoplanets. So it really did fundamentally change planetary astronomy. And the numbers just keep going up, and this is something that we're all going to be looking for a long time. And of course, the holy grail here would be: can we find a habitable planet around another star? And that's going to raise a whole bunch of other questions, and we're going to have to start looking for signs of life, and causing us to develop new techniques to look at planetary atmospheres and so on. So this is a fundamental change in how astronomers viewed the universe. Okay, I hope that answers the question, Hector.
Yeah, it does absolutely. Thank you, Paul. And yeah, you're completely right. It changed absolutely our cosmovision of what else is hiding beyond not just this Earth's atmosphere, but this galaxy that where we live. Thank you so much, Paul.
No worries.
Hello, Paul. I also have some questions.
Great.
How do properties of star influence this type of exoplanets that form around it? And what role does that star's habitable zone play?
Oh, that's a great question. I'm going to take back control of the screen here, Deb, because I want to go
Sure.
back to my HR
Yeah,
diagram,
sure.
because I think that addresses that. Just let me see if I can get this set up here. Share, and there we go. I'm going to go back into this HR diagram here. So there's a couple of different components to your question. First of all, the type of star. What is the how do the properties of the star influence the types of exoplanets that form around it? And again, we're in an area of speculation here. Okay, so let's take a look at our HR diagram. If you'll notice up here, we've got these kind of white stars. Okay, and down here we've got these kind of orange red stars, and our sun's kind of here. And I'm going to address these guys in just a second, but let's start up here. These are massive stars. These are much bigger than ours. They're much brighter. So there's a lot more material in it, and it's the hydrogen. They're hydrogen. They fuse that hydrogen to helium, and then wonderful things happen, and they sort of move kind of over this way a bit, because they're near the end of their life. But the point is, they do this very quickly. So normally, when a cloud forms of gas and dust forms to make a star, it takes a long time. It's like a big pot cooking. The gravity is slowly pulling the material together, and it's slowly starting to heat, and then you get fusion, and there's a period where it's not particularly really producing all that much energy. It's still consolidating, but it is technically a protostar. With stars like our sun, or even worse down here, that takes a really long time. But with these types of stars here, OBA stars, that sort of thing, these stars take a very short time to do that, which doesn't leave a huge amount of time for planetary formation. Or because the gravity is so intense, because there's so much material, there's probably also less, and this is speculative, less material left over to make planets. And then these stars end their lives quickly, and they go from sort of a normal star to a supernova, and then maybe to a black hole or to a neutron star, in a relatively short period of time. They move up here and then they go elsewhere. Okay. So for those type of stars, first of all, you don't have as long in the star's life to find the planets. Second of all, not as interesting. There may not be as many of them, and the planets are harder to find. Now, if we go over here down to these stars, this is more interesting. The stars are smaller. They take a long time to evolve, but they don't have as intense gravity. And there should be, and we're certainly finding this, leftover material to form planets. So you will see a lot more planets here. And that's what we're finding. And again, our methods may dictate our results to some degree. But, here we've got stars which are more conducive, we think, to planetary formation. And certainly the planets and the stars are going to stick around a lot longer. Now, the challenge with this is when you get into things like the habitable zone, that's the position of the star with respect to the sun and the amount of radiation it receives that would allow liquid water perhaps to exist on its surface. The challenge is for liquid water to exist, you need an atmosphere. These stars can be quite unstable, particularly early in their lives, and can blast away the atmospheres, or just are constantly producing flares with energetic particles, which might not be conducive to life. Now, evolution's pretty ingenious at solving problems like that, creating workarounds for life to form, we think. So, you might be able to find a fair number of these in the habitable zone. And I was actually listening to a podcast earlier today where they talked about Proxima Centauri, which is kind of down in this region here. It's the closest star. It's an M-type star down in this area to Earth. And it's got some planets. And the worry was that though there are planets in the habitable zone, they may not, they may be bombarded with radiation, have their atmospheres blasted away. But the thought is maybe that's not quite true. If the planet's just far enough away and geologically active, it might be producing enough volcanic activity to replenish the atmosphere, and then when the star stabilizes, you'd have something in the operating in the habitable zone. But again, we're getting to the edge of our theories here on planetary formation. I hope that answers the question.
Yeah, I mean, wow, this really gives us perspective on how it's such a big deal for us to be alive on this planet, for a life form to actually exist. It's
Yeah,
pretty,
absolutely.
yeah, pretty baffling. Okay, and
Yeah,
anyways, let's go to the next question. Okay, I'll just ask a question right here, if you don't mind.
sure.
Yeah, so what characteristics make an exoplanet potentially habitable, and how do scientists evaluate these factors?
Sure. So, well,
Yeah.
so the question is, what's habitable? I mean, Carl Sagan, in his book from 1972 called The Cosmic Connection, talked about carbon carbon chauvinism, meaning that we look for things that are like us. When we look for life, we're looking for carbon-based life. So the question itself basically has a bit of that chauvinism in it. That's a normal reaction to things like this. So when we define the habitable zone, we talk about a habitable zone for life like ours. Okay, meaning kind of carbon based, reliant on liquid water in some way, shape, or form. Liquid water is a very good media for encouraging chemical reactions, organic chemical reactions, sort of an organic chemistry model. Okay, and by organic, I mean specifically carbon, hydrogen, oxygen based. Okay, so to do that, you need liquid water. which basically means the planet has got to be a sufficiently distance away from the star that liquid water can, the heat on that, the temperature on that planet would allow water in its liquid state. Or could be something like Europa, I suppose, where you've got a planet which is basically an ice planet, but there's some sort of forces on that planet, tidal or thermal within the planet, which have a layer of liquid under it. So again, you would have to look for something that could exist in that kind of environment. So candidates for that would be a planet the right distance from its target star, from its host star, or a moon of a large planet at a good enough distance away from the star that you could get something like an icy shell with liquid ocean under it. So those are the sort of things we're thinking. But again, we're not really there yet, and that is based on a large number of assumptions. So I hope that it's probably not the most satisfying answer in the world, but it's the correct answer. And it's really kind of a word salad way of saying we're not really quite sure yet, but we're figuring it out.
Perfect. Perfect. Thank you.
Thanks again, Paul, for coming on tonight and answering all our questions. We really appreciate it.
No worries.
Great. So I will close us off for the night by doing our official outro now. Well, everyone, you have been listening to the Alan I. Carswell Observatory's monthly TeleTube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Hector, Dave, and myself, Maheen. Thanks again to our guest speaker, Paul Mackin, for a wonderful presentation. All of our programs are free, but if you would like to make a donation, see our website at yorku.ca/science/observatory. You can always connect with us on Instagram with the handle @yorkuobservatory and check out our website for show notes, content, updates, and contact info at yorku.ca/science/observatory. Thanks for tuning in, clear skies, and have a great night.